Now we can solve an example on the Snell's law, and let's say that we are having the angle of incidence here. The angle of incidence is equal to 60 degree for light, and we are having this material which is the incident material, and this is, let's say, we are having water, and for water the refractive index is this one. So I will say this is the refractive index of the incidence, and this is actually the refractive index for water. And this medium in which the light is entering is, let's say, the transmission is 1.52, and this is the refractive index of glass. So NW and NG, and we are asked to calculate that how much will be the transmission or the refraction angle. So we will write our equation that sine theta I divided by sine theta t will be equal to the refractive index of the transmission, so that will be the refractive index of glass divided by the refractive index of water. So here, putting the values, we will have this one is 1.52 and this one is 1.33, and the sine theta I will be actually equals to sine theta I. We know that it is sine 60, and sine 60 is equal to 1/2. So we are having this thing equal to 1/2, and putting the values, we will get that if I reciprocate this, then NW over this 1.33 divided by 1.52 sine theta I will this, so sine theta I will multiply. I can write sine theta t is equal to 1.33 by 1.52 multiplied with sine 60. So this is 1/2, and sine theta t, so this will become sine inverse, and all these values here, and I will get that this is equal to 49.3. So 49.3 is the transmitted angle, and I will have the theta t is less than theta I. So if it would have gone the same way, this much angle will be equal to theta I. Now theta t is less than theta I. So this angle is actually from the perpendicular, so this is this way. So this angle is now less than this, so the light is actually bended after the interface. We can solve another example here, and this example is, for example, we consider a helium neon laser. Then in this laser, the wavelength of this laser is lambda equals 633 nanometer, and this is in free space. This is in free space, while it is having a wavelength of 474 nanometer inside an eye. Inside a human eye, it is having a wavelength of 474 nanometer. Now, if I want to check that what kind of material is inside a human eye, then I will utilize this equation that N is equal to C over V, and C was equal to F naught lambda naught, and V was F and lambda. And we came to know that F naught and F was the same. So frequency is not changing, but only lambda naught and lambda. So lambda naught, it's in free space, it is 633, while 474 is inside I, and we get the N equals 1.34. And this is very close to the refractive index of water, because for water we are having 1.33. So we can from here guess that inside a human eye the water is very close to the natural water, and from here we can make a device such that if, for example, an infection in the eye occurs, then this will change. It will change from that of water, and this will give us the idea that inside the infection has taken place, and now the refractive index is not the same. Now if I want to check that whether the frequency remains the same or not, let me calculate the velocity of light inside this medium. So as I know the refractive index is C over V, so I can write that V will be equal to C over N, and now this V will be equal, C is 3/10⁸ meter per second, while N is 1.34. So this will give me 2.25 10 raised to the power 8 meter per second. So now this velocity has gone down, so the speed has decreased. If I want to check the frequency, now the frequency, which I call the frequency inside material, F, and then this is equal to V over lambda, and now V here is 2.25 10⁸ meter per second, and lambda here, the lambda that we measured inside the medium was 474 nanometer, and this is equal to 4.74 and 10 raised to the power 14 hertz. While if I want to check the frequency inside vacuum, then the V there is 3×10⁸, and the lambda is over there, which is 633 nanometer, and this will again come out to be 4.74 10 raised to the power 14 in hertz. So the frequency remains the same, while it is the wavelength that changes. So inside a medium, wavelength changes while frequency remains the same.